Hi, my name's Will, and I'm a data scientist. And part of my job is to explain particular topics within math and computer science to non-technical stakeholders. And with this video series, I'm attempting to do just that. And today, we're going to explore a topic on how LLMs work. So, in a very quick phrase, how to describe how it works is that LLMs are next token predictors. And what that means is that you'll ask it a question, which is the input text, it receives it, it breaks down your question. And when it's actually answering your question, what it's really doing is recursively trying to predict the next token or word that would best complete the answer. And so it does this repetitively until it builds out an answer that it deems complete and returns it to you. Now, after listening to this, you might think that it's a little trivial of a problem, but as we see in practice and daily usage, if this prediction is very powerful, then in reality, it's a quite powerful tool. A little history on this is before these kind of LLMs came out, we had a sequence to sequence architecture, which actually is what Google Translate uses in the backend. And so, how this works is that we use these RNN networks, neural networks, and it has this concept where you're feeding it text, and within the context vector, it will then digest what you have before and try to reproduce things similarly, word by word, in its output. But the key difference is that in this kind of input style, you have this concept of fading memory, in which the older the words or input cells are, the less impact it has on the answer generation part. And so it has like memory loss. And so that's good in some cases. But when you're processing long text, this kind of memory loss is not very beneficial in our case. And so that's why it's good for kind of short translations that you have, but not very good for very long term processing questions. And so the big change from that sequence to sequence to our modern LLMs is this kind of two parts. So there's this transformer network and the concept of attention. So just briefly to go through how the transformer works is that now we can feed everything in at once. So as you can kind of see, if we're translating the cat sat down, it actually intakes the entire sentence in at once, unlike what we saw in the sequence to sequence, where we're kind of passing it through one at a time. And in this, we have transformer network. You actually have two different layers. And so you have the attention layer, which is very powerful. And what it does is that it tries to look within your input and try to figure out what are the important parts, what are the descriptive parts, and what other parts are there just for linguistic reasons. And then in the feed forward layer, what it's really doing is taking what it processed in the attention layer and going back into its trained kind of model and processing and updating what it thinks the answer should contain. And so with this structure, everything's parallelized. And so you can kind of ingest a lot at once. And that's why you hear so much about, the massive scale of training data and stuff, because now with this transformer network, you can digest a lot through the model. And now in our similar example with the sequence to sequence, when it does try to produce an answer, it does that kind of recursive token generation, and it translates the cat sat down into French. And so when it comes to output, it's still not drastically faster in the sense that it does output one token at a time. But in the training, as we saw before, you can parallelize and do things at a much larger scale. And so, just to kind of summarize the massive difference between the older sequence to sequence method before LLMs and what's happening now in the transformer architecture of the current LLMs is that there's huge power in parallelizing things because of how we can ingest data now. And because of the data ingestion strategy, we also don't have this vanishing memory or memory loss when we are taking in very long responses. And now we have this core mechanism that we will explain later about attention. And with those things, it kind of makes the ability to scale these systems much greater and develop these really impressive LLM systems in which we all interact with today. And so now we're going to talk a little bit about how that attention layer works. And it goes through these kind of three different thoughts as it's processing your input. And so when it's going through, it will first look at each of the tokens, and based off this token, it will have this query index in which it's thinking, okay, what am I looking for? And a good example of that is for say, the bee is yellow in this sentence, right? If once you have the token of the bee, it will then say, okay, what are the things that we're looking for? This is the noun, right? There's maybe some things that describe it, like yellow, right? And if you look at the yellow token, you understand this is a color and that there's a noun called the bee. And so it will understand that, oh, okay, this is a color that is describing the insect of the bee, right? And so this is the query portion of how the attention network works. Key is obviously what it contains. Like I kind of briefly mentioned, like when you're looking at the bee, it understands like this is the noun, probably the subject of the sentence. And so there's some value in terms of that. And so when you take a look at those two values and you do the product of those two things, that's how they compute relevance. And so you can kind of see in that sentence that the doesn't really refer to a lot of things outside of just the grammatical necessity within the sentence. And so its relevance is going to be tuned low. And so the LLM understands like those kind of words are just there to be there because of the English language. But the important words are like the bee and yellow, right? And so that's how they update the value within the sentence structure of what things to be paying attention to in the input. And now, again, we're going to describe in the transformer network that you actually have this back and forth between paying attention to what you have and doing those computation, and also going back and trying to, with the knowledge that's been trained on, understand what's going on. And so how I like to visualize this is you first process the information in the attention block, and just like in those sci-fi movies where you're doing some kind of spaceship navigation, sometimes you have this kind of like 3D map you can zoom in and out in order to kind of pinpoint where you want to go. And that's kind of a similar thing of what's happening between attention blocks and feed forward blocks is that, okay, you're looking locally at what you're having as the input, then you're kind of going back out into your knowledge base to pinpoint the location that you think you want to go. Then you try to update what you have in order to figure out how to get there. And then you go back to your attention block and try to, again, with your updated information, re-observe what to pay attention to, and then do this repeated loop over and over again. And I think in GPT-3, we had around 96 layers. And so it would do this over and over again until it was ready to start generating an answer. All right, so now we're going to talk a little bit about how these things are trained. And at least in the earlier models, there was a big database called the Common Crawl. And what that did is, in fact, just scrape a lot of the different open web information and compile them into one clean location. And so this kind of served as the basis of training these earlier models. But now we've kind of eclipsed what the Common Crawl can provide, and we're actually going beyond what is publicly available. And so this is might be slightly outdated, but it is a good understanding of how what type of topics that the older LLMs are being trained on. And as you can see, it's quite a wide variety, but a lot of it is around business, tech, news, art, as you can see, things that kind of live a bit onto the internet. And not surprisingly, this Common Crawl project is scraping mostly English data. And so the performance of these LLMs are kind of best with English inputs. So, chinchilla scaling law is also related to the training concept, and that as these models get bigger and bigger, right, you also need to input more and more training material for it to scale to an optimal LLM performance. And so the law that people are observing is that of the millions and billions of model parameters, you need about 20 times the number of that in training tokens in order to get to a reasonably optimal performing LLM. So after training it, you get this raw model, right? But what happens is that a lot of these companies, such as Anthropic and OpenAI, also have this post-training component of the LLM. And so you can imagine the LLM has digested a lot of information and it's very knowledgeable, but essentially it has no work experience, right? And so it has to learn how to explain things to different people with different knowledge or an experience. And so what they do in post-training is they try to tune the model so that it can better translate the information that it has to humans, essentially. And there's three main strategies that it does this. So initially, uh, the most expensive way to do it is a supervised fine tuning. And what that means is that it we actually provide the model with actual good conversations or things that we would consider to be good answers to particular questions, and then have the model do more training so that as it generates the answer, it can tune the language, the styling to match that good example. But as you can imagine, that's very expensive because you have to generate those example conversations, and those can be like hundreds of thousands to millions of these conversations, and it's a very time-consuming thing to have humans do that. And so later on, we have two other ways, which is reinforcement learning from human feedback, and that's the example where AI may generate more than one response and ask a human which one it deems better. And I think for those of you who have used the Open AI web browser version, you kind of see that happen once in a while where it will ask you between choice A and B which response you deem better. And that kind of makes things a little bit more scalable because now you don't have mandatory manual conversations that you have to generate, but you still get kind of crowdsourced feedback from your users. And the last one, which is the least human involved, is that you have a similar process of reinforcement learning, but you get the feedback not from humans, but from other LLMs. And so how that works is very similar, but you have the LLMs then grade the responses and feed each other. And with that, you don't even need to feed it to your consumers, and you can just run this over and over again until you feel like the responses are good enough quality. And now, with all that training done, we're going to look a little bit into how exactly the answer is generated. We kind of mentioned briefly that it generates token to token, or in other words, word by word. But what it's really doing in inference is that it's taking in all your input tokens simultaneously and kind of runs it through, right, as a review of what's going on, runs it through all the transformer architecture of bouncing back and forth between attention layer and feed forward layers to kind of process what you're doing. And then when we're saying decoding and actually answering the question, what's really happening is that it's word by word generating the answer from what it understood in the question, and kind of doing that one step at a time. And that's reason why you get this kind of like a few minutes of thinking that the LLM needs to do, because it's in fact generating token by token the response. All right. And so when it's generating those next token predictions, there's a couple steps that actually happens, right? And so you can imagine there could be millions of different next possible words to the current response, and those are stored in logits, right? And so through the logits, then you do something called temperature scaling, and in these models, you can actually quote unquote raise or lower the temperature. And what temperature does is kind of allows for creativity, right? So essentially, it it scales the chances of things. It scales the tokens in which it thinks are less probable to be the actual answer, and scales it up a little bit. And so that way you have a chance of getting more interesting answers or creative answers in a sense. And so sometimes that's something that you might want for, like, for example, creative writing. But if you're answering math questions, you might tune the temperature down, and so that it more predictably selects the most correct token, right? And so after the scaling, there's actually two different ways of sampling which are the tokens that you want to select from. There's the more traditional top K filter, which just looks at the top K tokens that are the highest probabilities, and then only consider those, right? And select off those particular ones. And then in the newer strategy, you also have a top P, which doesn't go by a fixed number like K, but actually does more of a cumulative probability observation. And it takes, let's just say, the 90% probability answers, right? The top 90%, and then does the selection among those. And so what these filters are essentially trying to do is like really remove the chance of selecting something a little bit too far off from the normal, but also give enough of a selection that you don't just get the most predictable answers, because sometimes that most predictable answer is sometimes incorrect based off of context, right? So, okay. And now, last but not least, but now we just talked about how it's selecting the next token, but what it does under the hood after it doesn't show you token by token what it's generating. Usually it generates the entire thing and then shows you the response. And so what it can also do is generate n number of responses and score among those responses before returning it to the user. So it's kind of similar to the reinforcement learning with AI as a judge strategy that we talked about in post training, but this is kind of like a self judgment, and it's not actually learning from it, but more generating n number of answers and just selecting the best one to show you. The second newer thing that we've seen is a chain of thought, where it kind of breaks things into smaller steps. And so it's processing step by step. So technically, it thinks longer, but through this kind of breaking down of the response, it kind of generates better answers that way. Although it's a bit slower in this strategy. And last but not least, we have this kind of beam search, which is similar idea of best of n strategy. But what it's really doing is like it exploring those next token options, and just if it deems a particular response bad, it will kind of cut that off and not generate any continuing tokens for those kind of answers because it deemed it's not an actual good answer. All right. So thank you. That's a quick overview of how LLMs work, how they're trained, and how they kind of function under the hood. If you want to see more content like this, please like and subscribe.